Hi everybody, Mrs. Danielson here, and today we're going to talk about radicals and simplifying problems with your square roots in it. We're also going to talk about fractional exponents. All right, we have a lot to cover, so let's get started. I'm going to switch over here to my iPad and we will get some problems going. A lot to talk about today. All right, here we go. I put up here on my iPad the definition of a radical, and it's kind of complicated sounding, but it's actually pretty simple. Basically what they're saying, if we think about like a square root, which is the one we use most often, a square root looks like this. Square root of A equals B. Usually we don't write the 2 there, but it's implied. It's saying the square root of A equals B, that is equivalent to saying B squared equals A. That those two things are basically the same, they're equivalent, and that would be true for any root. It doesn't have to be a square root, it could be a third root, fourth root, fifth root, right? Let's say it was the fifth root of A, then that would be the same thing as saying B to the fifth equals A. All right, that's what it's saying in a more complex form, but that the square root of A equals B is the same thing as saying B squared equals A. We use a lot of square roots, but one thing we have to really watch for, and I want to talk about right off the bat here, is if I have the cube root of 8 equals 2. That means that the answer is 2 because it is 2 times 2 times 2. But if I had the cube root of -8, the answer to that would be -2, and that's okay because it's -2 times -2 times -2. But here's where we get a little bit confused sometimes. If I had the square root of -8, because we're only working with real numbers and we're not working with imaginary numbers, then this would not be defined. It's undefined. Right? And it wouldn't be defined for any even root. Like if I couldn't have the fourth root of -8, right? Because if I had like a negative number and I multiplied by itself 4 times, I would end up with a positive number, right? If I did -2 times -2 times -2 times -2, 4 negative 2's, it would be positive 8. It wouldn't be -8, right? So it's not defined. And it would be undefined for any even root. But it is defined, and it can be defined for odd roots. And so sometimes we tend to see a negative number in a root symbol, and we automatically think, well, that's not possible. I can't have a -8 in there because we're not doing imaginary numbers yet. Okay, but that's not true. Okay, if it's an odd root, you can have negative numbers inside there. It's okay. All right, just not if it's an even root. Okay, so don't automatically assume it's undefined if it's a negative number in there. Okay, well, we had some properties we learned about the other day for our exponents. We also have some really handy properties for our roots, and let's go ahead and talk about those. And these are really great. They do come in handy a lot, and there's 4 of them. These are our properties of our nth roots. Okay, the first one says if I have a number inside my nth root, I can actually take those and do them separately, those numbers inside, and I can do the nth root of A times the nth root of B. And you might be thinking, that looks more complicated. Why would I separate them into 2 separate roots? The reason you would do that is if you had like a really large number in your root and you didn't know what the nth root of that number was, but you could separate that large number into 2 smaller ones, and you knew the nth root of those 2 smaller ones, then you could calculate it. For instance, if I have -8 times 27. I don't know off the top of my head what -8 times 27 is, but it's a large number that I don't know what the third root of it is. I could separate those into -8 and 27, right? And I do know the third root of -8, and I do know the third root of 27, right? -2 and 3. So my answer is -6. Okay, so that's an example of when it comes in handy. And that actually happens a lot, right? Where you have like, what's the fifth root of some large number? And I don't know, but if you can separate it, you can solve it. Okay. Number 2 is kind of a similar thing. If you have the nth root of a ratio or a fraction, and I'm not super great at being able to tell what the nth root of a fraction is. There's a similar one for exponents where you have a ratio or fraction raised to an exponent. And I don't know what's, a fraction to the 5th power. But if I separate it into 2 separate ones, I can figure it out. Same thing here. If I have a fraction in there, I can separate it into 2 parts and then like do them individually. So say I have like the 4th root of 16/81. I don't know. What's this? What's the 4th root of 16/81? That's crazy. Who knows that, right? But you can separate that into 16 and 81, right? And I know what the 4th root of 16 is. It's 2, right? 2 times 2 times 2 times 2 is 16. And I do know what the 4th root of 81 is, because that's 3 times 3 times 3 times 3. So it's 2/3. And that's so much easier than trying to figure out what the 4th root of 16/81 is. Okay, so like both of those are great. Okay, number 3 is one you like hate to see in problems, but it's where you've got a root inside another root. Okay, hopefully you don't see this one a ton, but it does happen. When that occurs, you can actually multiply the 2 roots together and just combine them into 1, right? So this would be m times n, and just combine them into 1 single root. Okay. Let's say we have like a square root and then a 3rd root, and inside there is 729, and you're like, oh, I don't want to have to do the 3rd root of 729 and then take the square root of whatever that is. Too much work, right? You can just make that the 6th root of 729 and just do it like in 1 step, and that happens to be 3. You may not know that one off the top of your head, but at least you only have 1 step on the calculator to figure it out instead of having to do 2 problems. Okay. And the last one we're going to do today, and this one's almost like just kind of logical, right? If I have an exponent inside the root, and the root and the exponent are the same, it's like an a squared and then the nth root of it, and the 2nd root of it. If the root and the exponent are the same, you can just cancel them. Okay, so this would just be a. Okay, and that kind of makes sense, right? So let's say I had, it's a good example. Let's do the 3rd root -5 cubed, right? The answer for that would be -5, which makes sense, because if you think about this, this would actually be -5 cubed. And then the 3rd root would be 1/3. So the 3 and the 1/3 multiply together to make 1. And so it would be like -5 to the 1st power. Okay, so that law it's kind of logical, it kind of makes sense. But you know it's true, so now when you see that, you can just cancel them out and just leave with the value of a there. Okay. So let's just throw some of these together in a few practice problems and see what we can do. Okay, so the first one is a problem like this. Okay. Now some of you will be able to just look at that and just say, I know the answer. But let's look at it from applying the laws point of view here. All right, this would be the same thing as an x cubed times an x to the 1st, right? Because we add them together to get x to the 4th. And then this part right here is law number 4, right? We have a 3rd root of x to the 3rd, so the 3's cancel, leaving us with just an x. And inside, we still have that x to the first, and we can't really do anything with that. So that's our answer. Okay, we used two different laws there. We used a law of exponents, and then we used a law with the root. Okay, all right. Okay, I want to spend a couple minutes now and talk about combining radicals. And this is something that we haven't used much time on leading up to high school, but it's a really good skill to have. And actually, it's almost an algebra skill, really, than a radical skill. It's kind of both. But let's say we have a couple of square roots in our problem. And it's a problem where we need exact answers. So if you put this in a calculator and put in a square root of 32 plus a square root of 200, your calculator is going to give you a decimal, right? And a decimal is an approximation. It's not an exact answer. Okay, we want to leave it in square roots. We want to get an exact answer. Okay, so no calculators here, but we want to try to combine this into one instead of having two, okay, radicals. So to do that, we want to try to see if we can get the same radical out of both. And it helps to look at these and see, is there a perfect square that we can like pull out of the radical? For instance, the square root of 16 is 4. The square root of 25 is 5. The square root of 100 is 10, right? Those numbers that we can simplify out of the square root. So for instance, 32, that is 16 times 2. Okay, so there's a perfect square in there, the 16. Okay, and the second one is 100 times 2. There's a perfect square in there, 100. Okay, how that helps us is now when I take that 16 and I take it out of the square root, it leaves me with just a square root of 2. And over here, when I pull out that 100 as a 10, it leaves me with a square root of 2. And lucky, 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 we both have square root of 2. Those are like terms, just like when you're working with algebra and you had x's or you had x squareds, they're like terms. So you can combine them just like you combined x's when you were doing algebra. Okay, so this is how many square root of 2's? It's 16 square root of 2's, and you can just combine them. And now you have one term. Instead of those two radicals separate, you combine them into one. Okay. Let's do one more. Okay, we have two radical terms and we want to try to combine them into one. Okay, so again, you just look at them. Can I find a perfect square that I can factor out? Okay, so the first one has a 25 in it. So we're going to factor a 25 out of that. That's 25 times 5. And then the second one obviously also has 5s in it, right? That one is going to be 49 times 5. And that's nice because 49 is also a perfect square. So that's 5 root 5 and 7 root 5. They're like terms, and it gives us 12 root 5. And that's your combined radical for that problem. Okay. Nice. Okay, that's it on that. I just wanted to point that out and do a couple practice problems so you could see it. All right, don't put that in your calculator and get an approximation when you can combine them to get an exact answer. Okay, last thing we're going to talk about today is rational exponents. Oh, that's so scary, right? We're talking about exponents that are not whole numbers, exponents that are fractions, our favorite terms, exponents and fractions together, okay, in one thing. So we're talking about an exponent. The reason these combine, right, is if we're talking about, right, a radical, it becomes a fractional exponent, okay? What if we have something like this, right? What does that look like as a radical? It actually can do two different ways, right? We can say the nth root of a, right? So let me write one more intermediate step here. Okay, because this is 1 over n times m, right? It's that fraction times m. Okay, so we can write this two ways. It's going to be a radical times m. So it's going to be the nth root of a to the power of m. But you could also write it a little bit differently. You could do a to the m and then take the nth root. You can actually do either one, right? Just so you're taking the nth root and somewhere in there, whether it's in the radical or out of the radical, you're raising the a to the nth power, okay? So let's say we have a to the 2/3. Let's just show how either one of those will work. I know it seems kind of like, how is it possible that you could do it either way and still get the same answer? Okay, a to the 2/3, right, is going to be a to the second power and the 1/3. Okay, so we're going to do it both ways. See if we get the same thing. Okay, so that would be the third. Okay, and 8, and then square that. Or the other way would be 8 squared and then 1/3. Okay, so one has to square it on the outside, and the other one has to square it on the inside. Do we get the same answer? Okay, so the cube root of 8 is 2. And then down here, this would be the third root of 64. Okay, so 2 squared is 4. And the third root of 64 is 4. So you get the same thing either way you do it. Okay, you can pick which one you like more. Okay, all right, so now we have everything that we need for today. Let's combine some of this stuff into some problems. Okay, let's say, oh, one more thing. Let's just throw one more thing out there. Just to remind ourselves that we also have negative exponents. So now we have a negative fractional exponent. Okay, and the first thing I always do, like I said in our last video, I get rid of the negative first and then deal with the fractional exponent. So I would put this down here on the bottom, make it positive, and now deal with the fractional exponent, right? So it would be the third root of 125. And the third root of 125 is 1/5. Okay, all right, so now we've got it all together, right? We got our fractional exponents, we have our laws, we have negatives just to remind ourselves. Okay, let's put some of this together in just a few practice problems and then we'll be done. Okay, we'll start off with something kind of easy here. Okay, a couple fractional exponents. And now we're going to use our exponent laws here, okay, to simplify it. Okay, so all you have to do here is just add them. Okay, the only difference is they're fractions, right? Yuck. Okay, so it's 1/3 plus 7/3. So your answer would be a to the 8/3. Okay, it's not too bad, right? You should know there's going to be more. Okay, let's step it up a little. Let's do a to the 2/5, a to the 7/5. We're going to divide that whole thing by a to the 3/5. All right. What should we do first? Probably the numerator, right? That's going to be a, and you're going to add. Lucky for us, we have common denominators. So a to the 9/5 over a to the 3/5. And now we have the same base. We're dividing, so we can just subtract the exponents. Remember that from our exponent laws. So a to the 6/5. Okay. Okay. 2 more problems and we'll be done for the day. Okay, just continuing to step things up a little bit here. 3 halves. Okay, here we go. Raise everything in those parentheses to that fractional exponent and just do each part separately. And don't get overwhelmed with the fact that everything is raised to that exponent. Just do each piece by itself, right? So just do 2 to the 3 halves and then think A to the 3 times 3 halves, and then B to the 4 times 3 halves. And then just think about each part separately instead of being overwhelmed by the whole big picture. Okay. So 2 to the 3 halves, right? You can do either way. We showed you 2 ways to do it up above, right? I'm gonna write below it because I'm running out of space. That would be the square root of 2 cubed, okay? And then A, we're gonna multiply those together, right? And that's gonna be 9 halves. And then B, you're gonna multiply those together and you're gonna get 12 halves. Okay. That first part is square root of 2 times square root of 2 times square root of 2, right? Okay, the first two, square root of 2 times square root of 2, that's gonna equal 2, right? Square root of 2 times square root of 2. Okay, so that's going to give me 2 square root of 2. A, 9 halves, B, and 12 divided by 2 is 6. And I'm done. All right, so here's the deal. The next problem I'm going to put up is pretty big. I'm going to write it there, and then you're going to pause the video. You're going to solve it. And then you're going to push play and see if we get the same answer. But I really want you to try this next one on your own first. Okay? All right. You're going to try it independently. Okay? Challenge yourself. See if you can do it. If you don't get the same answer as me, that's okay. This one's kind of a biggie. It's got a lot going on. Okay? All right, pause the video and do this on your own. Okay, back. Let's see how we did. Okay, so you're going to take that 3 on the first part and distribute that through everything, right? Just bit by bit, right? So you're going to do 2 to the 3rd power. You're going to do x to the 3/4 times 3. You're going to do y to the 1/3 times 3. Just take it bit by bit, put that 3 and put it down on all 3 parts, okay? On the second fraction, there's a negative exponent, and now you know how I feel about those. I hate the negative exponents. Just get rid of that right now, okay? So to get rid of the negative exponent, move it to the other side of the fraction. Okay, so move it up top. All right, it's looking ugly still right now, I know, right? So let's do that multiplying on the exponents, try to clean it up. Well, 2 to the 3rd power, we know that's 8. So let's go ahead and write that down. Okay, x to the 3/4 times 3 would be x to the 9/4. Yes. Okay, and y to the 1/3 times 3 would be y to the 1st power. Yeah. Okay, and we're just going to multiply this through, combine them. Then we have a y to the 1st power and an x to the 1/2. Hey, what do you notice about the y's? Right, they cancel. That's nice. Okay, and now the x's, we have a 9/4 and a 1/2. We have to add those. And that's not a common denominator though. Right? We need a common denominator. So 1/2 with the denominator 4 is 2/4. Oh, I left my x out. There we go. It looked funny. So that would be x to the 11/4 force. Okay, did we get that right? Let's see. Right to the 1/3, y. All right, that should be our answer. Okay. Good job, everybody. Thanks for joining me. Have a good day.